Now, this is the third method for this particular integral. So I'm doing 3 videos for the 3 methods because there are quite many steps, particularly this method, method 3. It's a long, but it's very interesting. As it could be very, very good material for a calculus student. Okay, let me start with the expansion of a binomial, power series. Okay, now I know that log function, log 1 minus x is equal to negative x to the n over n, right? N equal to 1 to infinity. This is a power series for log function. And the power series for this, I think you must be familiar with. This is k equal to 0 minus k 2 k 2 k, right? Yeah. So I'm using 2 series for this integral. So this one is equal to 1, and it becomes very complicated. And this is because the first one is this one, sigma n equal to 1 to the infinity x n to the n. Then for this integral, k equal to 0 to infinity negative 1 to the k and x to k and dx. Wow, we have a double series. It's very complicated, but it's very interesting. It's very interesting and it's worthwhile to introduce this method. Now then, I take negative outside, sigma n equal to 1 to infinity 1 over n, and sigma k equal to 0. Now combine these two together. Combine these two. Well, because its power series is convergent in this interval, so I can exchange the operators. So this becomes x 2k plus n, right? This one and that one, and the dx. Yeah. So this one equal to negative n equal to 1 to infinity, and k equal to 0 to. So this one equal to negative to k, and this will be 2k plus n plus 1 x to 2k plus n plus 1 0 to 1. Wow. So we get this negative n equal k equal to 0, and this is 1 minus 0, right? So this is minus 1 to the k, and 2k plus n plus 1. Then I separate these fractions into partial fractions. So this is n equal n n equal to 1 to infinity, and the k equal to 0. And this one is just a over n plus b over 2k plus n plus 1. Well, then we determine AB, by comparing the coefficient. I think you can do it. I skipped that. Okay, the A is equal to 1 over 2k plus 1. B is equal to minus 1, 2k plus 1. See, nothing, just tedious calculation, determination of AB. So we have a negative n equal to 1, k equal to 0. All right, then take this out. We're done. This is 1 of n, and minus negative 1 over m, and m is equal to n plus 2k plus 1. Okay, we let this be m. All right, then what? Then, okay, I start with n first. Now, n is from 1 to infinity. So I let n is from 1 to big N first. Then take limit, n go to infinity. That will have this. Then my m will be from n equal to 1, right? N equal to 1 is 2k plus 2 to n plus 2k plus 1. Okay, I hope you follow me. See, this is the infinitive series. Now, at first, I let the series from 1 to big N, capital N. Then from N, we take limit to infinity to achieve these infinite series. So, okay. So my I is equal to, okay, this negative, I added here. So this becomes N from 1 and now I take this positive k first. K from 0 to infinity. And then 2k plus 1. And this minus 1 to the k plus 1. Because this one, I absorb this negative here. This negative one move here, become plus. So no more negative. I take this derivative. I take this take this series unchanged. That change, this has been changed. n from 1 to n. Okay, then n 1 of n, right? Minus uh, minus this 2 k plus 2, this m equal, right? Equal to m equal to n plus 2k. It's rather complicated. Yeah. Okay, I hope you follow that. Okay, this I separate this one is two series. Sigma this, sigma that for n. Huh? This one's out. I this one I'm not changed. I changed this power series. Power is from 1 to n. From 1 to n. And then m is from 2k plus 2 to n plus 2k plus 1. Right? Yeah. And this one is equal to, no, it's not equal to. I'm sorry. I will be equal to when this one goes to infinity. When this is taking n, it's not I. So, okay, now this is sigma k equal to 0. This is 2k plus 1 minus 1k plus 1. Now this one is a 1 plus 1 half plus 1/3, right? Plus somewhere reaches 2k. Well, somewhere 2k. Then 2k plus 1, right? Then somewhere reaches the end, which is n. Yeah. From 1 to n, capital N, capital N. So this is 1 to capital N. Somewhere must be 2k plus 1. And the minus, the first term is this. 2k is 2k plus 2, right? Then 2k plus 3. Then until, no, somewhere reaches the end. And keep going until n plus 2k plus 1. I hope you follow. This series is this. This series is that. Okay. Do you see all the cancellations? See? That means from this onward, cancel that. Cancel. These terms cancel with those terms. And from that onward, when n, capital N goes to 0, infinitive, then everything goes to 0. So my I is equal to when capital N is go approach to 0, approach to infinitive. Then this will be equal to sigma k equals 0 infinitive 2k plus 1 minus 1 to k plus 1. Everything is gone. When as n approaches to infinity, everything is gone. This is left over. 1 to 1/3 plus until 2k plus 1. Right? Because next term is this term. Cancel out. So then this one equal to this is equal to this one time times h to k. H is a harmonic number. Harmonic number is a 1, 1 over 2, 1 over 3, until 1 over 2k. The term before this one is 1 over 2k, and plus 1 over 2k plus 1. Yeah. From this to that one before this one is h to k, harmonic numbers. And this one times this one here is becoming two terms. One is k plus 1 over 2k plus 1 h to k. And the other one is h equal to 0, k equal to 0, negative 1 to k plus 1, 2k plus 1 square. Yeah. All right. Good. So this one we need to discuss separately. This one minus 1 to the k plus 1, 2k plus 1, h to k. This is a Catalan constant. Catalan constant. Well, negative, right? Because we're plus 1. So this one is this multiplied by negative 1. So it's a negative g. Okay. This one is a Catalan constant multiplied by negative 1 to the power 1. Okay. All right. So this one is equal to my I. Now, so we need to discuss, finally, we need to discuss this. Okay, to discuss this one's not easy. Well, we need to discuss this one. Okay, 0 in 2k. We discuss step by step. Okay, these are not easy, not very easy at least. Now, you know what's a harmonic number? Harmonic number is this, right? From n equal to 1 to k. That is a harmonic number. Now we need h of 2k. We need a summation. We need alternating. We need a denominator 2k plus 1. It's quite many steps to go. Okay, we know this. We know that sigma k equal to 1 to infinity hk times z to the k. Z is a complex number. To the power of k is negative 1 minus z log 1 minus z. That is available formula for this, for sigma hk zk. Now, I want h2k, not hk. So h2k zk z2k. Well, what to do. Now this is a every term is a to the even number power, right? 2, 4, 6, and so on. This is a 1, 2, 3, 4, 5. See, so we want an even number power. So what to do? We consider this h k z k k from 1 to infinity. That is a 1, 2, 3, 4, 5, and so on, all positive. Now this h k negative zk. This means that all the power is negative, even power is positive, because when even is become positive, order is negative. So add this one, all the order number power are cancelled out. The even numbers, you add it up, become twice. So I just multiply by this by half. Then this is equal to the even number power. Okay, I hope you get the idea. So this is equal to 1/2. This one, I use the formula, is a negative 1 minus z log of 1 minus z. This one, I use the formula 1 plus z, right? Log 1 plus z. That is equal to this. That is what we want. And we also need alternating. Alternating. We have this, it's not good enough. We need alternating. Alternating, okay, when z equal to ix, the z to 2k will be ix to the 2k one equals to I, yeah, I square, x square to the k, right? Yeah, so this is a negative 1 to the k. See, that comes alternating. That's what it meant. See, so the alternating h to k h z to 2k is equal to when z equal to ix. So ix log 1 minus ix minus 1 plus ix and log 1 plus ix. See, that will give us the alternating. Yeah. Okay, we solved problem the even number. We solved the problem of alternating. Now we need the denominator 2k plus 1. So we have to create 2k plus 1, the denominator. This could be done easily when you integrate. When you integrate from 0 to 1, you integrate 0 to 1, then I get a denominator. So this becomes sigma negative 1 to the k, right? H to k, z to 2k, and 2k plus 1, see? 2k plus 1, right? From 0 to 1. And equal to 2 integral 0 to 1, all those things, minus ix log I 1 minus ix minus log 1 plus ix 1 plus ix. So we have this. So when x equals to x, I'm sorry. When x equal to 1 is 1, when x is 0 is 0. So this 2k plus 1 minus 1 to the k, h2k is equal to minus integral log 1 minus x dx negative and negative half log 1 plus rx plus rx dx from 0 to 1. From 0 to 1. So we get what we want. Now, that is everything we want. So we just need to integrate step by step. Okay, this one, then, and that, and that one. So integral this one, log 1 minus ix, 1 minus ix dx. This integral, well, this integral is this, right? It becomes simply mean the d log of 1 minus x squared. This derivative is 2 times this one, times this derivative is this one. When you multiply 2I at the bottom, right? Cancel with ix. 2 cancel 2. So this one is equal to 2I negative natural log 1 minus x squared, right? From 0 to 1. Which is equal to negative 1I, 2I, right? What is this? 1 minus x. This becomes a log 1 minus I, right? Yeah, square. Good. So this one equal to negative 2I log. What's this? What is this? What is the log of 1 minus I? Log 1 minus I is a complex number, right? 1 minus I is this. This is 1, this is I, negative I. So this one is argument is quarter pi negative, right? So this is log the argument the modulus is root 2 times e to the negative quarter pi I. So this one is equal to log root 2 plus which is plus negative quarter pi I. Yeah, that is see, this is this one. So this one is equal to log 2 minus quarter pi I square. Yeah, good. Well, so now this one, and we have another one, right? 1 plus. For the same reason, this is equal to d 1 plus ix. No, this is equal to d log 1 plus x square. Yeah, and then with a 2 right here, right? Good. This one is equal to I log 1 plus ix square. Yeah, this one is equal to I. Well, root 2, right? The modulus is root 2, and the argument is a quarter pi. See, this one is equal to log 2 plus quarter pi r square. Yeah. Now then, well, we, then my I is equal to my I is this, right? Is it's very complicated. H2K1 is equal to negative half multiplied by this one and plus this one. Yeah, this one's a negative 2I log 2 minus quarter pi I plus this one log 2 minus quarter pi I square. Well, this is equal to quarter I. I take negative out. Then this minus this, right? This minus this. A square minus B square. A square minus B square is A square minus this is log 2 minus quarter pi I plus this. This is plus. I don't know, so somewhere there always wrong. Plus multiply by a minus b. This one minus that. So it's end up with for I. This will be 2 log 2 multiply. This will be log half pi. This cancel out is half pi. Negative. Yeah, so it's with the negative pi over. Yeah, log 2. Yeah, log, this is half log 2, so cancel with this 2. This is 8. I cancel out. Negative. Yeah, okay. No, this is not I. Okay, I is something else. I is equal to, we have two parts. Now. I couldn't find the words in my I. So my I is equal to, yeah. My I is this. I had it before. Okay. We calculate this one, right? This one is equal to, okay. My I is equal to negative, okay, minus 1. This is my I, and this is my, what is this? This is a, we have this, right? Yeah, this negative kh2k, net 2k over 2k plus 1 is equal to a negative, okay. We have to calculate this. Now, my I is, we have need a plus 1. So that means equal to negative that. So my I is equal to, I'm sorry, this messy. My I is negative that one because there's plus 1 here. It's negative. It's a negative of this. Minus a g. Okay? So it's negative that. It's a negative of. So end up with a positive. Well, I'm sorry. This is a very messy, and I hope you can trace back. Trace that. It's a very good method. It's a good method of maybe tedious, maybe it's long, but anyhow, it's good. It's good. And thank you.